Hello everyone, my name is John. In this video, I'll be teaching you how to make a third-person wall-running system in Unreal Engine 5 using C++. You'll learn how to create your own custom character movement component, something that is only possible with C++. You'll also learn about the essential 3D math behind wall running. Our system will support wall running on any surface at any angle, whether it's straight or curved. It will also include features like turning around corners and jumping off walls, so if any of that sounds interesting, please stick around. Before we get started, I just wanted to let y'all know that closed captions are available. Alright, let's get started. The first thing we're going to do is create a new project using the third-person template provided by Unreal Engine. This tutorial assumes that you're somewhat familiar with how the third-person character works, and that you're familiar with C++, but I'll explain things along the way, and please leave comments if you have any questions. We're going to choose C++ with no starter content, and I'm going to name this wall running tutorial. I'm actually going to close the project, open up the Visual Studio solution, and change some settings. I'm going to change the build to Development Editor. We're going to set Wall Running Tutorial as our startup project, and choose Start Debugging. You can choose to start without debugging, but it's good to use the debugger. I'll be closing the project and recompiling every time we make a change. Alright, so the first thing we're going to do is create our own custom character movement component class. It will be derived from the base character movement component class, and we'll be adding a wall running feature to it. As I mentioned earlier, this can only be done in C++. You can't create your own blueprint class that extends the character movement component. This is one of the many advantages of using C++ in Unreal Engine. I'm going to name this custom character movement component, but you can of course name it whatever you want. What we need to do next is make sure that the third-person character uses our new custom character movement component, and not the base character movement component. Let's open up the third-person character class. It might be named differently depending on how you named your project. We're actually not going to be using this default constructor. We're going to change it so it uses this special constructor that takes in an fObject initializer for a parameter. Now let's change the constructor's implementation so it adds the parameter. So what fObject initializer does is allow us to override components in the base class. In our case, we want to override the character movement component name so that a character class uses our custom character movement component. To do this, we're going to call the parent constructor, pass in the object initializer, but call a function called setDefaultSubObjectClass. We're going to pass in our character movement component class as the template argument, and pass in character movement component name as an argument into the function. This will change the character movement component for the third-person character. Oh, and don't forget to include the header file for our character movement component. Let's compile and run this. So if you open up the blueprint class for the third-person character, you'll see that it's unfortunately still not using our custom character movement component. It didn't update because this blueprint was made before we made changes to the C++ code. This happens sometimes when you're dealing with blueprints. We could create a new blueprint class based on our wall-running character class, but I'm not going to do that. To fix this, change any property in blueprints, press compile, then change it back to the original setting and press compile again. This is a very strange solution, but that's how things work in blueprints. Now with all of that out of the way, let's get started on the wall running code. Something that I want to mention is we're going to work on automatic wall running first. Later, we'll add the option to require the player to press a button to start wall running, but for now, the character is going to automatically wall run when they jump on a wall. Now how do we do this? Luckily, the A character class has something called a capsule component. This component is responsible for collision detection. This capsule component has a delegate called onComponentHit. This delegate fires off when the capsule hits something. If you're not familiar with how delegates work, think of it as an event. Different objects or functions can subscribe to this event. So when this event happens, it will notify all of its subscribers that the event occurred. The onComponentHit delegate will notify all of its subscribers when the capsule hits something. There's a great article written by Ben UI on how delegates work. I'll leave a link to it in the description. So what we need to do now is get our custom character movement component to subscribe to the capsule component's onComponentHit delegate. Let's navigate to the custom character movement component's header file. Now we're going to override the begin play function. This is where we will subscribe to onComponentHit. Let's create the definition for the begin play function and go to the CPP file. Now we're going to include two files. The header file for the aCharacter class, so we can access our character owner. And we're going to include the header file for the capsule component, so we have access to the character owner's capsule component. Let's call the base version of begin play, so we don't lose that base functionality. Let's get our character owner, call get capsule component. Then let's access that onComponentHit delegate. On that delegate, let's call addUniqueDynamic. This function is what lets this object subscribe to onComponentHit. We're going to pass the this pointer as the first argument. Now for the second argument, we need to pass in the memory address to a function that we want to bind to this delegate. We need to pass in the memory address to a function that we want to be called when the capsule hits something. Right now we don't have a function, so let's make one. Let's go to the header file. Let's make the function, and I'm going to name it onCapsuleHit. In order to bind this function to the onComponentHit delegate, we need to mark it as a U function. It needs to return void, and these are the required parameters. Let's create the definition. Let's go back to the addUniqueDynamic function and pass in onCapsuleHit's memory address. Now in the onCapsuleHit function, all we're going to do for now is print something to the screen, just to test if everything works so far. I'm just going to print this message. Let's compile and run this. Let's test this out. As you can see, the message prints to the screen whenever the capsule hits something. Awesome, we got it to work. Our next goal is figuring out how to check if we can wall run on the object that the character hit. What are the wall running requirements? For the first requirement, the character needs to be falling. The reason why is because we want the character to wall run when they jump or fall on the wall. It wouldn't make sense for the character to start wall running when they're on the ground. Our next requirement is the object or wall that the character hits needs to be wall runnable. What I mean by this is your character shouldn't be able to wall run on every single object. I mean, they can, but I don't think it'll be ideal. If a bird flies by your character, they shouldn't be able to wall run on the bird, even though it'd be pretty funny. Let's work on the first requirement. We're going to define a function called canWallRun. This function is going to return a boolean that indicates if the character can start wall running. So remember, for the first wall running requirement, the character needs to be falling. Luckily for us, the character movement component has a handy function called isFalling. So what we can do for now is return the result of isFalling. Later on, we'll expand on this function and add more wall running requirements. Let's go back to the onCapsuleHit function and test this out. What we're going to do for now is print wall run when the function returns true. Let's compile and run this. Let's test this out. Nice. As you can see, it only prints the message when we're falling and hit an object. It won't work when we fall on the ground. Alright, the next thing we need to do is implement our second requirement for wall running. The second requirement is that the object that the character hits should be wall runnable. We need to find a way to place an object in our level, like a static mesh actor, and mark it as a wall runnable object. There are multiple ways you can do this. The first method is you can place a static mesh actor in your level, add an actor tag on the static mesh actor, and name it something like wall runnable. The problem with this method is that it's not safe because actor tags are strings, which are prone to errors. When you check if an actor has a specific actor tag, you need to be really careful with typing out the tag, and make sure it's named exactly the same as the actor tag that was added to the static mesh actor. Actor tags are also outdated, so you should avoid this method. Another method is we can use gameplay tags, which is a safer and more versatile option. However, I think in this specific case for this tutorial, it would be overkill to use gameplay tags for something as simple as this. There's also a lot of setup that needs to be done in order to use gameplay tags, so I won't be using this method. The method that we will be using is with interfaces, and I'll explain along the way. Let's create an interface called iWallRunnableInterface. We will be using this interface to mark objects of another class as wall runnable. And that's pretty much all we need to do for this interface. We don't need to add any functions. Any class that inherits from this interface will essentially indicate to us that it's wall runnable. So what we're going to do next is create another class that is a wall runnable static mesh actor. This will be that class for the objects in our level that we can wall run on. It's going to derive from the static mesh actor class, and I'm going to name it wall runnable static mesh actor. Now what we're going to do is take advantage of multiple inheritance and have this class inherit from the wall runnable interface that we've created. Let's compile and run this. I'm going to create a folder called wallrun just to better organize things. What we're going to do next is create a blueprint class that is based on the wall runnable static mesh actor class we created earlier. For the default static mesh, I'm going to give it the cube static mesh, but you can set it as whatever you want. I'm also going to change the material. Alright, before we continue, I'm going to make some edits to this level. I'm going to do this to give us more room in the level, but you, of course, don't need to do this. I'll see you in a bit. Alright, what we're going to do next is place an instance of our wall runnable static mesh actor in our level. I'm going to scale it so it looks like a wall. This will be our first wall to test wall running on. Let's go back to the custom character movement.cpp file. What we need to do now is include the header file for the wall runnable interface. In the onCapsleHit function, let's get the other actor parameter and cast it to an iWallRunnable interface. If this cast is successful, that means the object that the capsule hit is wall runnable. This code is all we need to check if the character can start wall running. Let's compile and run this. Let's test this out. As you can see, it works when the character jumps on the object that inherits from the wall runnable interface. Let's test this out on a regular static mesh actor that doesn't inherit from the wall runnable interface. You can see that it won't work on this object, and that's exactly what we want. Now I'm going to add some code that improves performance by avoiding unnecessary casts every frame. If the capsule hits an object, and we've already determined that it isn't wall runnable, there's no reason to keep checking it over and over again every frame. Casts aren't cheap operations in terms of runtime, so what we should do is find a way to store the last actor we hit that isn't wall runnable. Let's go back to the header file. Let's create a pointer to an actor and name it prev non-wall runnable actor. It's going to be a weak object pointer because we shouldn't own the actor, and I'm going to mark it as transient because it shouldn't be serialized. Please leave a comment if you have any questions about this. In our begin play function, we're going to assign it to null pointer because it should be reset when the game starts. Now back to the onCapsleHit function. We're going to check if prev non-wall runnable actor is equal to the actor that the capsule just hit. If it is, we're going to exit out of the function. We're going to modify the code so when the cast fails, we're going to store the hit actor in prev non-wall runnable actor. Let's compile and test this out. As you can see, after we hit the non-wall runnable actor for the first time, it won't continue checking if it's wall runnable or not. The message only prints once. Awesome. So what's next? What we need to do now is initiate a wall run when it's time to do so. The way we're going to do this is first set the character's movement mode to a custom wall running movement mode. The engine has multiple movement modes for the character, which are stored in an enum. There's one for falling, swimming, flying, and so on. The one that we're interested in is the Move Custom Movement mode. This is what we're going to set the character's movement mode as. Let's go to the Custom Character Movement component header file. Let's create a function called init_wallRun. This function is going to be responsible for the wallrun initiation logic. Let's go back to the onCapsleHit function, and I'm just going to remove some code that we used for testing. Now, when this cast is successful, we're going to call init_wallRun. Let's go to init_wallRun, and what we're going to do is call the setMovementMode function. We're going to pass in moveCustom, which will let us use a custom movement mode. Now for the second parameter, it's asking for the specific custom movement mode that we want. Well, we haven't actually defined any custom movement modes yet, so let's do this now. What we need to do is create an enum for our custom movement modes. Let's create a header file for it. Let's move our mouse over to the Solution Explorer, right-click, Add, and click New Item. I'm going to name it custommovementmodes.h. Now we actually have to browse again to where we want the file to be. Let's move to the project folder, go to source, and go to the folder for our module. This is where the file is going to be. Our new enum is going to be similar to the eMovementMode enum that the engine provides. I'm going to name it eCustomMovementMode. It's going to be the size of an int. I'm going to mark it as a uenum and add blueprint type, just in case you want to expose this enum to blueprints. In order to use the uenum macro, we need to include the generated file. Let's name it custommovementmode.generated.h. And for our first enumerator, I'm going to create one for wall running and call it cmove_wallRunning. Let's also create another one for the max. You can add more custom movement modes, but we're just working on wall running in this tutorial. Let's go back to the custom character movement component.cpp file, include the header file for our custom movement modes. Let's go back to the init_wallRun function and add our wall running movement mode as the second argument for setMovementMode. And that's how you change the character's movement mode to a custom one. Now what's next? Our next goal for the wall run initiation is to rotate the characters so their orientation aligns with the wall that they're running on. Who's ready for some 3D math? Something that we need to think about is what side is the wall relative to the character. If the wall is more so on the left side of the character should turn to the right, and the opposite should happen when the wall is on the right side of the character. I think it would be a good idea to store some information that tells us if the wall that we're running on is on the left or right side of the character. Let's go to the custom character movement components header file. I'm going to define an enum right above the class definition, and I'll explain how it works in a bit. So this enum I named eWallRunSide will store information that will tell us if the wall is on the left or right side of the character. EWRS_left side for the left, and EWRS_right side for the right. Let's create a member variable with this enum. I'm going to name it wallRunSide. Now, how do we determine if the wall is on the left or right side of the character? With the power of 3D math, specifically dot products. When the capsule hits a wall, it retrieves this struct called a hit result. This hit result will give us information about the collision. The value in the hit result that we're interested in is a vector called impact normal. The impact normal is the normal vector extracted from the object that was hit in the area where the collision occurred. So if there's a wall and the character's capsule hits the wall in this area, then the impact normal will look something like this. If you're not familiar with what a normal is, just imagine it as a bunch of little spikes that stick out perpendicular to an object's surface. A normal is a normalized vector that is perpendicular to a surface. With that being said, let's store the hit result from the capsule hit. Let's go to the header file and define an fHitResult member variable and name it wallRunHitResult. Now let's go to the onCapsleHit function and assign the hit parameter to it right before the init_wallRun call. Let's go to the init_wallRun function, and what we're going to do is calculate the dot product between the character's right vector and the wallRunHitResult's impact normal. Let me explain how this works. The dot product between two normalized vectors tells us how similar the two vectors are. If the result is 1, that means the two vectors are pointing in the same direction. -1 means they're pointing in opposite directions. If the result is positive, that means the angle between them is less than 90 degrees. If the result is negative, then the angle between them is greater than 90 degrees. So how does this help us? If we take the dot product between the impact normal and the character's right vector, and the result is positive, then the wall is on the left side of the character. If the result is negative, that means the wall is on the right side of the character. So now that we have the dot product result, named right proj wall normal, we could use it to get our wall side. So if right proj wall normal is positive, then we're going to assign EWRS underscore left side to the wall side member variable, else we're going to assign EWRS underscore right side to it. Alright, great. Now what we need to do is find the initial wall run rotation for the character. Let's create an F rotator and name it target rotation. We should actually create a function that will be responsible for calculating the wall run rotation. Let's go to the header file, create a void returning function called calc wall run rotation. It will take a reference to an F rotator, which will be the result of the calculation. Let's call it out wall run rotation and create the definition for the function. Now how do we get our wall run rotation? How should our character be oriented when they're wall running? Rotations can be described with 3 basis vectors. In our case, the character's forward, right, and up vectors when wall running. They should align with the wall and look something like this. So what we should do is find these 3 basis vectors. Let's find the right vector first, because it'll be the easiest one to find. If the wall is on the left side of the character, the right vector should be the same as the impact normal. So what we should do in our calculation is create a vector called y, or right, and set it appropriately. So what this code does is check if the wall is on the left side. If it is, assign the impact normal to y. If the wall is on the right side, then assign the negated impact normal to y, which is the impact normal flipped in the opposite direction. Alright, we found the y basis vector. Now what we should do is find the x, or forward basis vector. Now how do we find this? The x basis vector should be 90 degrees away from the y vector. When you're trying to find a vector that is perpendicular, or 90 degrees away from another vector, this problem would be a good candidate for using the cross product. When you take the cross product between two normalized vectors, the result is another vector that is perpendicular to the two vectors. Right now we have the target y vector. What we can do is perform the cross product between the y vector and the character's up vector, and that will give us the x vector that we need. Let's add this to our code. So x is equal to the cross product between y and the character's up vector. We should also normalize this vector just to be safe. Basis vectors should be normalized. Great. We actually have all of the information that we need to define our F rotator that will represent the target wall run rotation. The F rotation matrix struct has a helpful static function called make from xy. We're going to call it and pass in our basis vectors. This function will return an F matrix that is another representation of the rotation. If you didn't know, in 3D math, it's common to store rotations with matrices. What we're going to do with the returned F matrix is convert this to an F rotator. And that's all we need to do for the calc wall run rotation function, for now at least. Let's head back to the init wall run function. What we need to do now is smoothly rotate our character to the target rotation over time. There's a nice function in the ukismet system library that can help us with this. Let's include the header file for the ukismet system library. We need to call a function called moveComponentTo. What this function does is translate and rotate a component over time. For the first parameter, it needs the component we're moving. We're rotating the character owner, so we actually pass in the character owner's root component for the first argument. For the next parameter, we need to pass in the target location that we want the component to translate to. We won't be translating the character, so let's just pass in the character's current location. For the next parameter, we need to pass in the target rotation. Let's pass in our target rotation. The third parameter is called beaseout, which is a boolean indicating if we want to slowly exit out of the interpolation. I'm going to pass in true, but you can try out false if you want. If you don't know what interpolation means, it's the process of smoothly transitioning a value between 2 points over time. So in this case, we're interpolating the character's rotation to the target rotation over time. The next parameter is called beaseend, which is a boolean indicating if we want to start the interpolation slowly. I'm going to pass in true. The next parameter is a float called overtime, which is the duration of the interpolation. So how long do we want it to take for the character to rotate to the target rotation? I'm going to make it last for 0.2 seconds, but it's totally up to you. I'm going to put this value in a constant called move duration, just for clarity. The next parameter is called b_shortest rotation path, which is a boolean indicating if we want to always use the shortest path for rotation. This will be true. For the next parameter, we're going to pass in an enum called eMoveComponentAction. The enumerator that we want to pass in is called move, because our action is moving the component. Now for the final parameter, we need to pass in a struct called fLatentActionInfo. This struct is helpful if we want to perform some kind of action over multiple frames. This is useful for us if we want to perform an action or call a function once the character finished rotating with the moveComponentTo function. We will be taking advantage of this because there's a function we need to call once the rotation is done. Let's create an fLatentActionInfo instance and call it latentInfo. For the first constructor parameter, it needs the linkage. We're going to pass in 0. For the next parameter, it needs a UUID. We'll pass in this macro called index_none. For the next parameter, it needs the name of the function that we want to be called when the action is complete. I'm going to pass in a function name called onWhileRunInitComplete. This function doesn't exist yet, but we'll create it in a moment. For the final parameter, it needs the callback target, which is the object that we're calling the function on. We need to pass in this. Let's pass in our latentActionInfo as the final argument. Alright, what we need to do now is create the onWhileRunInitComplete function that we added to our latentActionInfo earlier. Let's go to the header file. Let's declare the onWhileRunInitComplete function and have it return void. So in order to have this function work with the latentActionInfo we created earlier, we're actually required to mark this function as a U function. Let's create the function's definition. Now, before we define this function, let's go back to the header file and define a boolean member variable called b_whileRunInitiated. What this variable will do is let us know if the while_run initiation is in progress or not. The reason why we need to know this is because we might want to disable certain functionalities when the while_run initiation is in progress. Let's go back to the init while_run function and set b_whileRunInitiated to false. Now let's go to the onWhileRunInitComplete function and set b_whileRunInitiated to true. Alright, that's all we need to do for the while_run initiation. Let's compile and test this out. As you can see, when the character jumps on the wall, they rotate to align themselves to the wall. Let's try to angle this wall a bit and see if it'll still work. Awesome, it still works. Great job, guys. We finally completed the code for the while_run initiation. It was a lot of work, but we got it done. So what's our next step? Our next step is getting the character to actually while_run. Crazy, right? Before we start writing any code, let's talk a bit about how the code in the base character movement component class moves the character. So let's go to the character movement component header file and search for the movement update functions. If you look here, you can see that there are different functions for each of the movement modes, and these functions are responsible for moving the character. There's one for walking, flying, swimming, and so on. The one that we're interested in is this Fizz custom function. The reason why is because we're using a custom wall running movement mode. Let's go to our custom character movement component definition and override the Fizz custom function. Let's call the base version of Fizz custom. Now what we're going to do is add a switch statement for the custom movement modes that we have. Right now the only case we have is for our wall running movement mode. So if the current custom movement mode is cmove_wallrunning, we're going to call a function called fizzWallRunning. This function doesn't exist, so let's create it. Let's go to the header file, create fizzWallRunning, which takes in a float called delta time and an int32 called iterations. So this function here is going to be responsible for the wall running logic. So the first thing we need to do in this function is check if certain requirements are met in order to continue running this function. If not, we're going to exit out of this function immediately. Our first requirement is the wall run needs to be initiated. If the wall run isn't initiated, then we're going to exit out of the function with an early return. We need the character to finish rotating to the initial wall run rotation before wall running. Our second requirement is the delta time parameter needs to be greater than this macro called min tick time. If you don't know what the delta time parameter is, it's the time in between the current frame and the last frame. This time is important to make games run consistently no matter how fast or slow your machine is. For example, if a character in your game needs to run at 5 miles per hour, delta time will help make sure that the character won't run faster than 5 miles per hour on a faster computer at a higher frame rate. We'll use this delta time parameter again in the future. Let's continue. What we're going to do next is perform a line trace. If the wall is on the left side of the character, the line trace is going to start at the location of the character and shoot in the direction to the left of the character. If the wall is on the right side, then it will shoot to the character's right. What this will do is query the wall that we're running on and extract the normal vector that we need from the wall in order to calculate our wall running rotations. It'll also help us answer other questions, like if there's still a wall next to the character that they could run on. Let's code this up. Let's create an f vector called traceStart, which will be the origin of our line trace. Let's set it to the character's location. Let's create another vector called traceDirection, which will be the direction of our line trace, and it'll be influenced by the side that the wall is on. Let's create another vector called traceEnd, which will be the line trace's endpoint. It's going to be traceStart plus traceDirection, and there's a value that we need to multiply this with, which is the length of the line trace. I'm going to call this value wall's search trace distance. This variable doesn't exist yet, so I'm going to declare it as a member variable for this class. Let's go back to the header file and declare this. Let's go back to the .cpp file and go to the begin play function. I'm going to set the wall search trace distance to double the size of the radius of the character's capsule. I did some experimentation and found that this value works well. It'll make the line trace long enough to detect walls. Let's go back to fizzWallRun and add the line trace call. So this function performs the line trace starting from trace start to trace end, and it'll store the result in our while_run_hit_result member variable. The last parameter is the collision channel that the trace is going to use. There are multiple collision channels, but the one that's commonly used to trace objects in the world is called the visibility channel, which we are passing into the function. Let me know if you have any questions about collision channels. Alright, let's use the result of the line trace. If the line trace gets a hit, that means the character is still next to a wall to wall run on. If it doesn't get a hit, the character should stop wall running, but let's deal with that later. Let's rotate and move the character along the wall. Let's create an F rotator called target rotation. Call calc wall run rotation and pass in target rotation, similar to what we did before. Now that we have our target rotation, we need to smoothly rotate our character to the target rotation. And we're going to be using a different method than we did previously. We're going to use this function called rInterp2. This function will be called every frame, and what this does is give us the interpolated rotator that is in between our current and target rotation. In our phase while running function, our target rotation is changing every frame, so this rInterp2 function will help smoothly rotate the character to the target every frame. For the first parameter, it needs the current rotation. Let's pass in the character's rotation. The next parameter is the target rotation. For the next parameter, we need to pass in delta time. For the final parameter, it needs a float called interp speed, which is the speed of the interpolation, or how fast we want the character to rotate. What I'm going to do now is create a member variable that will hold this value. Let's go back to the header file and define a float member variable called while run rotation interp speed. For the default value, I'm going to give it 5.0. This value works well. I'm going to mark it as a U property so you have the option to edit this in Blueprints. You need to make sure that this value is high enough because you want your character to rotate fast enough. This is especially important for curved walls where the character needs to turn quickly enough. Let's go back to our phys while running function and pass in the while run rotation interp speed to the rInterp2 function. Now we need to set the character's rotation as the result of this function. Now that we have the character's rotation, we need to calculate the character's velocity. The direction of this velocity is going to be the character's forward vector. Now we need to multiply this with the speed. So what is our character's while running speed? Let's define a member variable for that. Let's go back to the header file and define a member variable called while run speed. I'm going to set 550 centimeters per second as the default value, but it's totally up to you. Let's go back to phys while run and multiply this direction with the while run speed. Now that we have our velocity, we need to create another vector that will be our velocity adjusted by delta time. Recall back when we talked about delta time. In video games, movement needs to be frame rate independent, and this delta time parameter helps us achieve that. Our character's velocity shouldn't be affected by frame rate, so multiplying this velocity with delta time will help the velocity become frame rate independent. Now that we have the adjusted velocity, we need to call a function called safe_move_updated_component. This will move our character and also handle collision. For the first parameter, we need to pass in our adjusted velocity. For the next parameter, it wants the new rotation of our updated component, which is our character. Let's pass in the interp target rotation. The next parameter is called bsweep, which is a boolean indicating if we want to check for collisions. This is going to be true because we don't want the character to move through other objects in the level. And for the final parameter, it needs an f_hit result. I'm going to pass in our while run hit result. Alright, let's compile and run this. Now the character is while running. Let's angle the wall a bit and see if it still works. And it still works. Now let's check if it works with curved surfaces. I'm going to create a new instance of our wall runnable static mesh actor and set its static mesh as a cylinder. Oh no, it doesn't work. Let me explain why. When the character wall runs at a high speed, it can move so fast that they move completely away from the wall in a single frame. If that happens, the character will stop wall running because they're no longer next to a wall. The way we can solve this problem is by moving the character closer to the wall before the character moves forward. This way, the character is constantly hugging the wall no matter how fast they're going. So what we need to do is move the character close to the wall. Let's create a vector called character to wall. It's going to be the wall run hit results impact point minus the character's location. The impact point is the location where our line trace hit the wall. We should move the character to the impact point so they're hugging the wall. The character to wall vector is what we need to move the character. Let's call safe move updated component. Let's pass in character to wall. Then let's pass in the character's current rotation. Then true to check collisions. Then the wall run hit result. This is going to be done first before the other moves. Let's compile and run this. Now the character is properly wall running on curved walls. Awesome. So what's next? The next thing we need to do is figure out how to exit out of a wall run when the character is no longer next to a wall. I think the character should start falling when they're done wall running. Let's switch the character's movement mode to the falling movement mode. Let's call set movement mode and pass in the falling movement mode. Let's test this out. Nice, the character now exits a wall run when they're at the end of a wall. What we're going to do now is fix an issue that I haven't addressed yet, which is when the character wall runs, the player still has the ability to move the character. This shouldn't be able to happen. We should disable this when the character is wall running. Let's go over how the character moves around when you press the WASD keys. Let's go to our third person character class implementation file. Let's go down to the function called move. This function is bound to the WASD keys, and the way it moves the character is by calling this function called add movement input from the pod class. Let's take a look at this function's definition. Now this function calls another function from the pod movement component class called add input vector. What this function does is move our character based on our input, which is converted to a world space vector. Now our custom character movement component inherits from this upod movement component class, so we can override this add input vector function to disable movement when the character is wall running. Let's go to our custom character movement component's header file and override the add input vector function. I'm making it public since the base version is public. Here's the function signature. Now let's create the definition. In this function, we're going to check if the character is not wall running. If they're not wall running, then we're going to call the parent version of this function. This is essentially saying if the character is wall running, then do nothing. Don't move the character. If the character is not wall running, then execute the function as you did before. The isWallRunning function doesn't exist yet, so let's create it. Let's go to the header file, define a bool returning const function called isWallRunning. We're going to return true if the character is using a custom movement mode, and if the custom movement mode is the wall running movement mode. Let's test this out. So as the character is wall running, I'm trying to move the character with the WASD keys, but nothing's happening, and that's exactly what we want to happen. Great. Alright, what's next? I think the next thing we should do is add the ability to jump off walls. So currently, when the character is wall running and we press the jump button, which is the spacebar, the character can't jump off a wall. Now why is that? If we go to the character movement component's definition, there's this function called canAttemptJump. Let's check out this definition. This function allows the character to jump as long as these conditions are met. What we should do is override this function so it lets the character jump when they're wall running. Let's go back to our custom character movement components header file and override the canAttemptJump function. So in this function, it should return true if the character is wall running, but there's another condition we need to include. The character can jump when wall running only if the wall run's initiation is complete. We don't want that initial rotation to be interrupted by a jump, so in this scope, we need to return B wall run initiated. If the character isn't wall running, then return the base version of this function. Let's test this out. Now our character can jump off walls. Alright, the next thing we need to do is add a cooldown to our wall running system. After the character finishes a wall run, they should wait for a brief moment before being able to wall run again. If the player is able to wall run immediately after exiting one, it won't look natural. So let's temporarily disable wall running once the character stops wall running. Let's go to the header file and define a float member variable called wall run cooldown duration. This is going to be the cooldown time before the character can wall run again. I'm going to initialize it to 0.7 seconds, but it's up to you. Now we need to define an F timer handle that will help us set a timer for our cooldown. Let's name it wall run cooldown timer. Now we need to find some way to be notified when the character switches to a new movement mode after wall running. Luckily, there's a function in the character movement component class called onMovementModeChange that can help us. Let's take a look at the function's definition. So what this function does is notify when the character movement mode changes, as well as the previous movement mode that was active. Let's override this function in our custom character movement component. Let's first call the base version of this function so we don't lose that base functionality. Now let's check if the previous movement mode was our wall running movement mode. If it is, we're going to call a function that will set our cooldown timer. Now let's go through the steps for setting the cooldown timer. First we need to get the world. Then we get the world's timer manager. Then on the timer manager, we need to call the set timer function. For the first parameter, it needs the timer handle, so let's pass in our wall run cooldown timer. Then it needs the duration of the timer. Let's pass in wall run cooldown duration. And the final parameter is a boolean called nbLoop, basically asking us if we want to loop the timer. We need to pass in false. The next thing we need to do is prevent wall running when the cooldown timer is active. Let's go back to a function we made earlier called can_wallRun. We need to add some code in this function that will return false if the wallRun cooldown timer is active, because the character shouldn't be able to wallRun if the timer is active. Let's get the world. Let's get the world's timer manager. And on the timer manager, let's call the isTimerActive function. Let's pass in our wallRun cooldown timer. We need to actually wrap this in parentheses and negate it because we want this to be false when the timer is active. So to recap, the function grants the ability to wallRun if the character is falling and if the wallRun cooldown timer isn't active. Actually, let's do better and refactor the cooldown code into a function. The function will be called isWallRunCooldownActive. Let's create the function. Let's add the cooldown check we made earlier. And that's it. Let's test this out. So right now I'm spamming the jump button to try to exit and enter a wallRun repeatedly, but it won't let the character wallRun again until the cooldown period is over. Excellent. Alright guys, how are y'all doing? Please leave a comment if you need any help. Alright, so the next thing we're going to do is implement corner turning. Once the character meets a corner, the player should be able to turn around the corner, similar to Insomniac's Spider-Man or Sunset Overdrive. There are two types of corners. There's an inner corner, which is a corner where two walls meet inside of a space, and there's an outer corner, which is a corner at a space's exterior that points outwards. Let's handle inner corners first. So the way we're going to handle inner corners is we're going to perform a line trace in front of the character, pointing in the character's forward direction. This is going to happen every frame when wallRunning. If the trace gets a hit, then that indicates that the character is at an inner corner. Let's go to our Fizz wallRunning function, and we're actually going to check for inner corners before everything else. If there's an inner corner, we're going to perform some logic, then immediately exit out of the Fizz wallRunning function. So all of the code that we wrote below this point was for detecting if there was a wall besides the character. Now we're going to write some code to check for inner corners. Let's create a vector called traceStart, which is the origin of the line trace. Let's set it to the character's location. Let's create another vector called traceDirection, which will be the character's forward direction. And let's create another vector called traceEnd, which is the endpoint of our trace. It's going to be traceStart plus traceDirection, and traceDirection is going to be multiplied by our wall search trace distance. Now we're going to call the function that performs the line trace. If the line trace gets a hit, that means an inner corner was found. For now, let's just exit out of the wallRun and add an early return. Now there's actually something we need to fix. We've already defined these vectors earlier when we were checking if a wall was next to a character. Let's modify some code to get rid of the redefinitions. What I'm actually going to do now is add some code that will visualize our line trace. This is totally optional, and obviously don't include this in your final game. This will just help us clearly see how our line trace works. I'm going to call a function called drawDebugLine, which will draw our line trace. It needs the world for the first parameter. The second parameter is the starting point of the line. Let's pass in traceStart. The third parameter is the endpoint of the line. Let's pass in trace end. The fourth parameter is the color of the line. It's up to you, but I'm going to make it red. Now the next parameter is a boolean called bPersistentLines, which indicates if we want the line to have a lifespan. We're going to pass in false because we're going to be drawing this line every frame. So we're going to draw the line, then destroy it the next frame, then draw it again, and repeat this every frame. There are other optional parameters, but I'm just going to leave it at that. Let's test this out. I'm going to duplicate this and rotate it so the two walls form a corner. As you can see, the line trace is visualized with the red line, and it's casting in the character's forward direction. Once it hits the wall, the character stops while running. So the character shouldn't stop while running when they're at a corner. They should turn in the direction of the next wall where the corner is formed. Let's go to our header file and let's define a function that handles the case when the character is at a corner. I'm going to name it handle while run corner, and it returns void. Let's go back to our phys while running function and call handle while run corner when we're at an inner corner. Alright, so what should we do when the character meets a corner? One thing is the character should rotate in the direction of the other wall. To calculate the target rotation, we just need to call the calc while run rotation function like we did before. Simple, right? Now the way we're going to rotate the character is by using the move component to function like we did in the beginning of the video. We're going to pass in the character's capsule component for the first parameter. Now the second parameter needs the location where we want to move the character. We do need to find this target location because the character needs to move to the other wall. Let's calculate this target location. Let me explain how this works. So we want to move the character to the other wall. A good location would be to move the character to the line trace impact point because it's the area on the wall where the line trace got a hit. The problem is if we move the character to this location, the character would end up inside of the wall. So we should move the character away from the wall. So we should move the character again in the direction of the impact normal. And the size of this movement should be the character's capsule radius because that's the width of the character. So if we move the character here, then the character would be against the wall. This calculation gives us that location. Now let's pass that target location into the move component to function. Let's pass the target rotation as the next argument. We're going to ease out of the interpolation. We're going to ease into the interpolation. Now for the duration of the movement, let's create a member variable for this. Let's go to the header file and define a float member variable called while run corner turn duration. I'm going to set its default value to 0.3 seconds. Let's expose this to blueprints too. Let's go back to the move component to function and pass in the corner turn duration. We're going to force the shortest path. We're going to pass the move component action. Now for the final parameter, it needs a latent action info. Let's create one like we did before. For the callback function, we're going to call a function called onTurnAroundCorner, which we'll create in a moment. Let's pass this latent action info as the final argument. Let's create the onTurnAroundCorner function that will be called when the character finishes turning. Let's go to the header file and create it. Don't forget, we need to mark this as a U function because it's used by the latent action info. Alright, so before we add any code to this function, let's define a boolean member variable called b is turning around corner. This will indicate that the character is turning around a corner. The reason why we need this is to block the phys_while_running function from executing when the character is turning around a corner. Let's go to the init_while_run function and set the variable to false. Let's go to the handle_while_run corner function and set the variable to true because the character is turning. Let's go to the phys_while_running function and add the condition here that this function can't continue when the character is turning. If the character is, then exit out of this function. Now let's go to our turnaround corner function and set the variable to false because it's no longer turning. Let's test this out. Now the character is turning when they're at an inner corner. I'm going to change the angle of the corner and test if it still works. It still works. Alright, so the next thing we're going to do is handle outer corners. This is going to be a bit tricky, but we'll get it done. So far, we've written code to check if a wall is besides the character. If there is a wall, the character should run on it. We've also written code to check if the character is at an inner corner by checking if there's a wall in front of the character. If all of this fails, it would be a good time to check if the character is at an outer corner. So the way we can do this is by performing a line trace besides the character that points in the opposite direction of where the character is facing. So if the character is here, the line trace should start here and cast in the opposite of the character's forward direction. If it gets a hit, that means the character is on an outer corner. Let's go to the phys_while_running function, and before we write our outer corner detection code, let's modify some code that we wrote earlier. So here, when it finds a wall besides the character, we're going to exit out of the function when the movement logic is done. We're also going to remove this code here. So all of the code below this point is to check for outer corners. So the first thing we need to do is find the starting point of our line trace. If the wall run side is on the left side of the character, then the trace should be on the left side. If the wall run side is on the right, then the trace should be on the right. So for the left side case, this code here finds the location on the left side of the character, and it's going to be the wall search trace distance away from the character. The code for the right side is the same, but in the opposite direction. So for the direction of the line trace, we want to point it behind the character, so it's going to be the character's forward vector, but negated. For the trace's endpoint, it's going to be similar to the previous line traces that we've done, so it'll be the size of our wall search trace distance like before. Let's perform the trace. So if the trace gets a hit, then the character found an outer corner. We should call the handle_while_run corner function, And once that's done, we should exit out of Fizz while run. If everything we've done up to this point fails, the character should stop while running, so let's set the movement mode to falling here. Let's test this out. As you can see, the character now turns around outer corners. There's actually an issue that'll happen if you're building corners the way that I did with these walls. So when we meet this corner here, the character is going to get stuck. The reason why is because the other wall is blocking the character from moving. So in reality, if you're creating something like a building to wall run on, don't make it like this. Don't shove multiple static meshes together. The object you're wall running on should be a single static mesh. So what I'm going to do right now is create some type of building structure using the cube grid tool and use it as a single static mesh. You should ideally just get a 3D model from an external source and import it to your level, but I'm trying to keep this tutorial as simple as possible and free of cost. I'm not going to explain how I'm using the cube grid tool because this is not a tutorial for that. Just try to follow along with what I'm doing. I won't skip any steps. Alright, so I created an instance of a wall runnable static mesh and applied the static mesh that was made with the cube grid tool. Let's test this out. The character now properly turns around outer corners. Let's test both inner and outer corners. Awesome, it works. So what's next? What I want to do next is make the wall running a little more interactive for the player. When the character meets a corner, instead of automatically turning the character around, the player should turn the character using the WASD keys or the stick. So for example, if the character is wall running and the character meets a corner, and if the camera is pointing in this direction, the player should press the D key or move the stick to the right if they're using a controller. So let's first find a way to get the player's input. So let's go to our third person character's CPP file, and let's go to the move function. So if you remember, the way the character moves based on the player's input is with this function. This function calls another function called addInputVector, which gets the player's input as a world space vector and moves the pawn based on that input. Remember a while back, we overrode this function to disable movement with input when wall running. What we should do is when the character is wall running, we should store this world vector parameter. Remember, this vector is the player's input in world space. So when the character is wall running, we should store this world vector so we can turn the character around a corner based on this vector. Let's go to the custom character movement components header file and define a vector member variable called wallRunControlInputVector. Let's go back to the addInputVector function in the CPP file and store the world vector in the wallRunControlInputVector when the character is wall running. So if the character is wall running, store world vector in the wall run control input vector. Else, call the base version of this function. Something else we need to do with this vector is consume it. So once we're done using this vector for the current frame, we need to reset it to an empty vector. What we need to do is override a function called tickComponent. This is a function that is called every single frame for the component. We need to override it to reset the wall run control input vector at the end of the function. Let's go back to the header file and override the tickComponent function. Here's the function signature. Let's first call the base version of this function. Then let's empty out the wall run control input vector. There's actually one more place where we need to empty the vector, and that's in the init wall run function. Alright, so let's use this vector for our corner turning. Let's go to the handle wall run corner function. So what we need to do is find the direction of where the character needs to turn. So for example, the character should turn this way in this example. The way we can find this vector is by converting the target rotation to an F rotation matrix. Converting it to an F rotation matrix will help us extract the basis vectors of the rotation. We need the forward direction of the rotation, so the x-axis basis vector. We can call a function on the F rotation matrix called getUnitAxis. So which axis do we want? We want the x-axis, so we need to pass in this enum called e-axis. And the enumerator we need is x. So now we need to check if the player is trying to move the character in the direction of this corner turn direction vector. We have the player's input in world space called wall run control input vector. What we can do is compute the dot product between the corner turn direction and the wall run control input vector, and the result will tell us how similar these two vectors are. So this code is saying if the angle between the corner turn direction and the wall run control input vector is less than 90 degrees, then the player wants to turn the character around the corner. If you want the maximum angle between these two vectors to be smaller, you can change this 0.0 to the cosine of whatever angle you want. Leave a comment if you want me to explain this more to you. Now what we need to do is turn the character only if this boolean is true. So let's wrap this in an if statement. So if the player wants to turn the character, then turn the character. If not, the character should stop while running. Let's test this out. So right now, I'm holding the D key to try to turn the character to the right around this corner. Great, it works. Let's try this again, but this time I'm not going to press anything. Great, the character stops while running, which is exactly what we want. Let's try this one more time, but I'm going to hold the A key. Now the character stops while running because I was supposed to turn the character to the right, not the left. Awesome. Alright, in terms of the main wall running system and logic, we're pretty much done. All of the code that makes the character wall run is complete, other than the animations, but we'll get to that later. Right now, we're going to work on adding the option to turn off automatic wall running. So you have the option to require the player to press a button or a key for the character to start wall running. Let's go to the custom character movement components header file, and let's define a boolean member variable called bAutoWallRun. So this boolean will let the component know if the character should automatically wall run or not. If this is true, the character will automatically wall run when they jump on a wall, similar to the Spider-Man games. If this is false, the player needs to press a button while in the air to wall run. If this is false, a function needs to be called to enable and disable wall running. The functions will be defined in this class, but should be called from the character class. Let's make this editable in Blueprints. Let's define another Boolean member variable called b_wants_to_wall_run. If this is true, that means the character is attempting to wall run, or the player is pressing the input that should activate wall running. False otherwise. Let's declare a public function called wallRunStart. It's going to return void. Alright, so what this function is going to do is enable wall running. This function is public because it should be called from the owned character class. Calling this function means the character or player wants to wall run. So let's set b_wants_to_wall_run to true. However, it only makes sense to call this function if automatic wall running is turned off. If automatic wall running is turned on, then the character should wall run no matter what. So what we need to do is exit out of this function if automatic wall running is turned on. Let's go declare another function called wallRunStop. So this function is pretty much doing the opposite of the last function. This should be called when the player releases the input. Something else we're going to do in this function is make the character stop wall running if a wall run was in progress. Great, we're done with those functions. We need to modify other functions to take these booleans into account. Let's go to the begin play function and set b_wants_to_wall_run to false, since it should be false when the game starts. We also need to modify our can_wall_run function. We need to add the condition that the character can wall run if automatic wall running is turned on. If automatic wall running is not turned on, then b_wants_to_wall_run needs to be true. Alright, so we're done adding the automatic wall running option to the custom character movement component. Right now I'm going to show what you need to do if you want automatic wall running turned off for your third person character. If you want automatic wall running turned on, then you just need to set the b_auto_wall_run boolean to true, and that's it. You can skip the rest. But now I'm going to show the steps needed if you want automatic wall running turned off. We're going to bind input to the wallRunStart and wallRunStop functions. I'm going to bind it to the shift key, so the player needs to hold the shift key to wall run. Let's go to the header file and declare an input action called wallRunAction. This declaration is going to be similar to the other input actions. Now let's go to the CPP file and bind this input action to the wallRunStart and wallRunStop functions. Let's go to the setUpPlayerInput component function, get a pointer to the custom character movement component instance that the character is using, and check if the pointer is valid. So what we need to do now is bind the wallRunStart and wallRunStop functions to the wallRunAction. Let's call the bindAction function, pass in wallRunAction as the first argument. For the second parameter, it needs an eTrigger event. We're going to pass in the started enumerator. For the next parameter, it needs the memory address of the object that owns the function that is bound to this input. Let's pass in the pointer to the character's custom character movement component instance. For the final parameter, it needs the memory address to the function that needs to be bound. We want to bind wallRunStart. The next thing we're going to do is bind the wallRunStop function to have it be called when the player releases the input. Let's copy and paste this. Let's change this to completed. For the final argument, we're going to change it to the memory address of while run stop. Let's recap. So when the player starts or presses the input, while run start is going to be called. When the player releases or completes the input, then while run stop is going to be called. Let's actually refactor this cast into a function. Let's call this function getCustomCharacterMovementComponent. Let's create this function. So this function is going to return a pointer to the CustomCharacterMovementComponent instance, which we need to cast from a character movement component to our custom character movement component. Let's compile and run this. Let's go to the folder where all the input actions are. They should be in content, third person, input, then actions. Let's create a new input action called IA_while_run. Let's open it. Let's add triggers to this. The first trigger is going to be set to pressed. The second trigger is going to be set to released. So pressing the input will start the input action, and releasing it will complete the input action. Let's save and close this. Now let's find and open the input mapping context that our third-person character is using. It should be in the input folder, and here it is, IMC_default. Let's add our IA_while_run. Let's bind it to the shift key. This can actually be whatever you want. Let's save and close this. Now let's open the blueprint for our third-person character. Let's access the beAutoWhile_run boolean that we created earlier. Let's uncheck it to set it to false. Now let's look for the while run action we made earlier. Let's set it to IA_while_run. Let's press compile. Let's save and test this out. So right now I'm holding the shift key and the character's while running. Now I'm going to let go of the shift key and now the character stops while running. Now I'm going to try to jump on the wall without pressing the shift key. And the character doesn't while run. Awesome, we got it to work. Great job, guys. Alright, so the next thing we need to do is address an issue that we have with our camera when turning around a corner. When the character turns around a corner, the camera gets pushed into the wall, which doesn't look good. So we need to find a way to move the character's camera away from the wall when they're turning around a corner. Most of the code will be done in the third-person character class, because our custom character movement component's primary purpose is to move the character. It shouldn't be responsible for manipulating the camera. With that being said, let's go to the header file for our custom character movement component. We need to find a way to notify the character owner when the character is turning around a corner. A way we can accomplish this is with delegates. We can declare a delegate for corner turn notifications. Above the class definition, let's use a macro function that starts with declare delegate. This is what is used to declare a non-dynamic single delegate. If you're not familiar with how delegates work, again, I'm going to refer you to Ben UI's article on delegates. The link is in the description. You can also leave a comment if you want me to clear things up. Alright, so I want this delegate to have two parameters. I'll explain why in a moment. We need to end this name with the number of parameters we need. For the first parameter of this macro function, it wants the name of our delegate signature. It's Unreal's convention to prefix the delegate signatures with an F, and it's going to be called f_on_corner_turn_begin signature. This delegate is going to be for when the character starts turning. Now for the delegate's parameters, I want the first one to be a vector representing the direction of the turn. This will let the subscriber, or the character in this case, know the direction of the turn. For the second delegate parameter, we should inform the character if the corner was an inner or outer corner. I think it'll be a good idea to create an enum that represents the corner type, similar to the wall run side enum. Let's create an enum called corner type. This corner type enum has an enumerator for inner corners and outer corners. Now what we're going to do is set the third parameter for our corner turn delegate to be the corner type. So did the character turn around an inner or outer corner? Now let's create a delegate signature for a delegate that will notify when the corner turn has completed. Let's name it F on corner turn end signature. This delegate will be a non-dynamic single delegate with no parameters. What we have to do now is create member variables for our delegates for our character to access and subscribe to. Let's create a public member variable of our on corner turn begin delegate. Let's call it on corner turn begin. Let's create another one for the on corner turn end. Alright, so on quarter turn begin is responsible for notifying the character when the quarter turn started, and on quarter turn end is responsible for notifying the character when the quarter turn finished. Alright, let's go to the CPP file and go to the code where a quarter turn starts and finishes. Let's go to our fizz while running function. This section of code here is where an inner quarter turn happens, and this section of code here is where an outer quarter turn happens. We should send that information to the handle while run corner function. Let's go to the header file and change the signature of the handle while run corner function and add a parameter for the corner type. Let's go back to the fizz while running function and pass in the corner type. We're going to pass an inner corner here, and we're going to pass an outer corner here. Let's go back to the handle while run corner function, and here is where we're going to notify the subscriber with our delegate that the corner turn has begun. Let's get the on corner turn begin variable and call the function execute if bound. This function is how non-dynamic delegates notify their subscribers. Alright, so remember, for the first parameter, it needs the vector of the corner turn direction. Let's pass in corner turn direction. For the second parameter, it needs the corner type. Let's pass in corner type. Now let's notify the character when the corner turn finishes. It should finish in the on turn around corner function, so let's go there. Now let's notify the character with the on corner turn end delegate. Alright, so that's all we have to do on the custom character movement component side. Let's update the third person character class so it subscribes to these delegates and moves the camera during their corner turn. Let's go to the header file for the third person character and let's override a special function called post initialize components. This is where we'll be subscribing to the delegates. So this post-initialize component function is a part of the actor lifecycle and is called before the game starts, but after all of the actor's components are registered and initialized. You should use this function when you need access to a component right after it's been created and initialized. This is a great place to access the character's custom character movement component and access those delegates that we need. Let's call the base version of this function. Let's get a pointer to the character's instance of the custom character movement component. Now let's get the on quarter turn begin delegate. Let's subscribe to this delegate and bind a function to it by calling bindUObject. Let's pass in this as the first argument. Now the second parameter needs the memory address to a function that we want to be called when the notification fires off. The memory address to the function that we want to bind to this delegate. Let's pass in a function called onCoderTurnBegin, and we'll create this function in a moment. Now let's do the same for the onCoderTurnEnd delegate, and let's bind a function called onCoderTurnEnd, which we'll create in a moment. Let's go to the character's header file, and let's create the onCoderTurnBegin function. Don't forget, we need this function's parameters to match the parameters of the onCoderTurnBegin delegate. So the first one is the quarter turn direction. The second parameter is the quarter type. The problem here is that the quarter type enum hasn't been defined in this file. We can solve this problem by forward declaring the enum. This is basically telling the compiler, hey, trust me, this enum does exist. Its definition will be included in the CPP file, just like forward declaring a class. Let's go back to the onCoderTurnBegin function declaration and add the quarter type parameter. Let's create its definition. Now let's create the onCoderTurnEnd function. It'll have no parameters because the delegate doesn't require it. Alright, let's recap. Here in the post-initialized-components function, we had the third-person character class subscribe to the onCoderTurnBegin and onCoderTurnEnd delegates. We also bound functions to the delegates. The onCoderTurnBegin function will be called when the quarter turn begins, and the onCoderTurnEnd function will be called when it ends. Alright, so how should we move the camera when the character turns around a corner? We have the quarter turn direction, which points in the direction of the next wall. I think that the camera should point in this direction, but rotate it away from the wall by some amount, maybe 45 degrees away from the wall. We can get this new camera direction by converting the quarter turn direction vector to a rotator and rotate it by 45 or negative 45 degrees. The way we're going to rotate the camera is by adding a camera lock-on mechanic. We can have the camera lock on to the new rotation when the quarter turn happens. Another thing I want to mention is we're not going to move the camera if we're turning around an inner corner, because our camera issue only happens with outer corners. So let's execute the camera logic only when it's an outer corner. Let's go to the header file and declare a rotator called target camera rotation. This will be the rotation that the camera will lock onto. Let's go back to the onCoderTurnBegin function and let's set the target camera rotation to the quarter turn direction, but we need to convert the quarter turn direction to a rotator. Now we need to rotate the rotator away from the wall by an offset. I'm going to make the offset 45 degrees. Let's create a double for this offset. Now the way we can rotate the rotator by this offset is by adding or subtracting to the rotator's yaw. So something like this. However, when the character is making a left turn, we need to subtract the offset from the yaw. If the character is making a right turn, we need to add the offset. How can we find out if the character is making a left or right turn? We can calculate the dot product between the character's right vector and the quarter turn direction. If the result is positive, then it's a right turn. Left if it's negative. So when the character is making a left turn, let's subtract 45 degrees. And let's add 45 degrees when the right turn happens. Now what we need to do is create a Boolean member variable that indicates if the camera should lock onto something. Let's go to the header file and create it. Let's call it B camera lock on active. Let's go back to the on quarter turn begin function and set the boolean to true because we should lock on to the target camera rotation now. Another thing is when the character finishes a quarter turn, the camera should stop locking onto its target. So let's go to the on quarter turn end function and set the boolean to false. Something we need to do is set this boolean to false when the game starts, because the camera shouldn't lock onto anything at the start of the game. Let's override a special function called begin play. This begin play function is called right when the game starts, so we should set B camera lock on active to false here. Now that we've initialized the camera lock on, how do we rotate the camera so it faces our target? This is something that we need to do every frame. There's a function that is ran every frame called tick, so we should override the function and rotate the camera there. Here's the signature for the function. Alright, so we need to check if the camera lock on is active. So the way we're going to rotate the camera is with the rInterp2 function. If you remember a while back, this function is used every frame to interpolate from one rotation to another. This function needs an interpolation speed, so let's actually define that first. Let's go to the header file and define a float member variable called camera lock on interp speed. I'm going to set its default value to 7.0. I'm also going to make this editable in blueprints. Let's go back to the tick function and find the target rotation with the rInterp2 function. So for the first parameter, it needs the current rotation. There's something I need to mention. We actually won't be rotating the camera directly. We're going to be rotating the spring arm component that the camera is attached to. Also, this third-person character class is set up in a way where our controller rotates the spring arm component. So for the current rotation, we're going to call a function called getControlRotation. For the next parameter, let's pass in the target camera rotation, which is the rotation we want to attempt to interpolate to. The next parameter needs delta time, and the next parameter needs the interpolation speed. Let's pass in the camera lock on interp speed. The next thing we need to do is set the controller's rotation to the new rotation. Let's call a function called getController to get our controller. And we want to set the controller's rotation, so let's call a function on the controller called setControlRotation. Let's pass in the interp target rotation. Alright, so that's basically all we need to do to lock our camera onto the target rotation. And once again, in our case, the target rotation is going to be the corner turn direction rotated away from the wall by 45 degrees. Let's do better and refactor this code into a function. Let's call the function rotate camera to target. Let's define the function and add in the code that we wrote earlier. Alright, let's test this out. So I'm going to turn around an outer corner. As you can see, the camera gets pushed away from the wall by 45 degrees. And nothing is done to the camera with inner corner turns. Awesome. Alright, we're done with the camera mechanic. So the final thing we need to do is add animations to our character and make it play a wall running animation when the character is wall running. So in order to add animation logic, we're going to spend the majority of our time in the animation blueprint that our third-person character is using. Before we start working on the animation blueprint, we need to create and expose some functions to blueprints from our custom character movement component. we need the animation blueprint to be able to access some data from the component. Let's go to the header file for the component and mark the isWhile_running function as blueprint callable. We're going to create another function called getWhile_run_side that returns the while_run_side member variable. Let's mark it as blueprint callable. The final function we're going to define is called isTurningAroundCorner, which returns a Boolean member variable b_is_turning_around_corner. Once again, let's mark it as blueprint callable. Oh, and one more thing. Let's go to the eWhile_run_side enum and change the display name to while_run_side. This way the name will be more clear in blueprints. Let's compile and run this. Alright, so the animation blueprint that our third-person character uses is called ABP Quinn. This animation blueprint derives from the ABP Manny animation blueprint, so we'll be working on ABP Manny. So the first thing we'll do here is create some variables that'll store while-running information. Let's create a Boolean variable called isWhile_running. Pretty self-explanatory. Let's drag and drop all the variables we'll be creating into this essential movement data category, because it is essential movement data. Let's create another variable called while_run_side, and the data type will be the while_run_side enum we created in C++. Let's create one more variable called isTurningAroundCorner, which is a boolean. So here in the event graph, we need to update the variables that we've made every frame, and there's a blueprint function that is ran every frame called updateAnimation. We'll be updating the variables here, but first, we need to update this variable that was made called characterMovement. Right now, its data type is a reference to the base characterMovement component. We need to change it so it uses our custom characterMovement component, so let's do that. Let's compile. Now we have some errors because the event graph was using the base characterMovement component. Let's remove this, and let's cast this reference to the custom characterMovement type. Now let's set the movement component variable as the result of the cast. Let's compile, and now the errors are gone. Let's go to the update animation function and update our variables. Let's set the isWhile_running boolean first. Let's get a reference to our custom characterMovement component, and let's call the isWhile_running function that we created in C++. Now let's set the boolean to the result of the function. Now we actually have to go to this sequence node and add that to the sequence. Oh, I forgot to connect the output to the input. Now let's update the while_run_side. Again, let's get a reference to the movement component, and now we're going to call the getWhile_run_side function. Let's set the while_run_side variable as the result of the function. Let's add this to the sequence. Now let's update the isTurningAroundCorner variable. Let's call isTurningAroundCorner. And let's set it the way we set the other variables. Let's compile. Now let's use these variables to control our while-running animation logic. we need to go to our Atom graph and open this state machine called main states. Let's create a state for our while running logic. Let's name it while running. The only way to get to a while running state is from a falling state, so we need to add a transition from the for loop to the while running state. We should also transition from the jump state. We can actually do better. Rather than having these links, let's get rid of them and create a state alias for our while running state. If you're not familiar with state aliases, they're just another way to reduce clutter and improve organization when creating transitions between states. So what states are allowed to transition to the while running state? You can transition to the while running state from the for loop and jump state. So let's click on the state alias, go to the details panel, and check the two states. Another question we need to ask is what states can the while running state transition to? You can only fall after a while run, so let's go to the two falling state aliases detail panel and check while running. But remember, you're most likely going to change things for your own game specifically. Okay, so how can this state transition to the while running state? What is the while running state's transition rule? The only rule is that is while running variable needs to be true. So let's add that transition rule. We also need to add another transition rule for the line state. Is falling needs to be false, but is while running also needs to be false, because if the character's while running, they're also not falling. But we want it to transition to the while running state, not the line state. So let's add that. Alright, so before we add any more code to the Atom graph, there are a few important things that we need to add to our project. Can you guess what they are? Yes, you've guessed it. We obviously need to add the while running animations. If you go to the description of this video, you'll find a GitHub link to the repository for this project. There you can download or clone the repository so you have a copy of this project. And in the project, you'll find the while running animations. They'll be on the content/whilerun/animations folder. You can migrate or import those animations to your project. I also want to apologize in advance because the animations aren't great. I decided to animate these myself because I wasn't able to find any high quality while running animations online that were free or affordable. I'm also not an animator by any means. I've only watched a few animations tutorials and proceeded from there, so I'm very sorry if the animations aren't good. With that being said, our next step is to add animations to the while running state we made. Let's open the while running state and add them. The animations are called while run left and while run right. The left one is for when the wall is on the left side of the character, the right one's for the right. So what code do we need to add here that will determine the animation that should be playing? The animation that will be playing should depend on the while run side variable we made earlier, so let's get that variable. And what the code should do is choose to play the left animation if the while run side variable is equal to the left side and the right for the right. Let's use this blend poses node that will blend animations with the while run side enum. Let's add pins for both sides. We need to hook the while run side to the active enum value and connect the correct animation to its associated enum value. We can use the while run left animation for the default pose. And don't forget to connect the blend poses node to the output animation pose. Also, don't forget to make sure these animations are looping. Let's compile. So there's one more issue that we need to fix. The while running animation doesn't seem to work well with this control rig, and I honestly don't know why. When this control rig is connected, the while running animations don't look the way it should. I've tried adding the condition here that the IK trace shouldn't be executed when while running, but that doesn't seem to work. So what I'm going to do is add code that skips the entire control rig when the character's while running. Please let me know in the comments if you know a better solution, or if you know how to get these while running animations to work with a control rig. Let's cache the main state's result. and only use the control ring addition if the character is not wall running. Let me know if you have any questions about what I just did. Let's compile and test this out. As you can see, the character plays the wall run left animation for left side wall runs, and the character plays wall run right for right side wall runs. Yay, we did it, guys. We're finally done with this entire wall running system. It was a lot of work, but I hope it was worth it. You guys did a great job, and thank you so much for sticking around. This was my first ever tutorial, so I hope I did okay, and I hope you guys found this video informative. Leave a comment if you have any questions, concerns, or want to say absolutely anything. Thank you for letting me be a part of your game dev journey, and take care. Bye-bye.